Linear probabilistic modeling is a statistical method, often used by engineers, which examines the relationship between an independent and dependent variable by approximating their relationship with a line. The location of each dependent data point y is given as a function of the independent variable x using this formula. Beta naught is the y-intercept of the linear model and is added to the equation for each data point. Each beta value is related to the concept of slope and is essentially the ratio between the dependent and independent variables. Here's an example of how a linear probabilistic model might appear, with each data value appearing as a scatter point and the regression line appearing through the center of the points. The distance between the data value and the line is known as epsilon. This distance is called the random error and is a normally distributed variable with a mean value of 0. If you were to subtract the epsilon value from each data point in the model, you'd be left with a perfect straight line. To gain a better understanding of how this type of modeling works, I'll take a look at how it applies to variables that have a linear relationship in nature. Hooke's law, which applies to springs, is one such example of a simple linear relationship. The distance for the spring to stretch, represented by x, can be thought of as an independent variable, while the force required, F, is dependent on x. The relationship between x and F is given by Hooke's law, F equals negative kx. Here's an idealized example of how an engineer testing the performance of a spring could study the relationship between F and x using a linear probabilistic model. In this example, the data points are perfectly linear, but in practice, an engineer should find that epsilon is normal with a small variance, since observed error should be relatively small in a perfect linear relationship. For a more detailed look at linear probabilistic modeling and the ways it can apply to engineering, I'll take a brief look at an example from the field of mechanical engineering. When an engineer is working with a material, he or she will observe and analyze some of its properties over a range of temperatures. One of these properties is often thermal conductivity. An engineer working with rhodium might observe that for the given temperature range, the relationship between temperature and thermal conductivity is roughly linear. He or she could then use this information to construct a model by using temperature as the independent variable and thermal expansion of the metal as the dependent variable. Here I've created the model for the thermal conductivity of rhodium as a function of temperature. Using this model, it becomes clear that the relationship between temperature and thermal conductivity is approximately linear. It also may be observed that the mean epsilon value is 0. I trust this video gave you a basic understanding of linear probabilistic modeling and an idea of how it can be applied in an engineering context.